Hey everyone, and welcome to another video in the Paper Explain series. In this one, we are going to talk about this paper, Chain of Verification Reduces Hallucination in Large Language Models, which was written by Meta AI in collaboration with ATH Zurich. The paper starts by saying that the generation of plausible yet incorrect factual information, termed hallucination, is an unsolved issue in large language models. Which is true. Also, at the time that this paper was written, in 2023, in September, as it is today, it's still an unsolved problem at the time this video was recorded. And they go on and say that we study the ability of language models to deliberate on the response they give in order to correct their mistakes. Okay? And they develop the chain of verification, or COVE in short, method whereby the model first drafts an initial response, then plans verification questions to fact-check its draft, then it answers those questions independently so the answers are not biased by other responses, and then finally it generates its final verified response. And they show in their experiments that COVE decreases hallucinations across a variety of tasks, from list-based questions from Wikidata, closed-book multi-span question answering, and long-form text generation. Then, in the introduction, they go on and talk about hallucinations and their contributions in this work, and they give a wonderful figure that gives an overview of their approach, which is the chain verification or COVE method. So first of all, given a user query, which is this one, where they say name some politicians who were born in New York, and then the model answers to this prompt with what it considers to be politicians from New York, like Hillary Clinton, Donald Trump, Michael Bloomberg, and so on. And as you probably know, not all these politicians are from New York, so the model hallucinates and gives factual inaccurate responses. And to improve the LLM response, the authors do the following. They perform another prompt where they plan the verifications and they ask where each of these politicians were born. For instance, where is Hillary Clinton born? Where was Donald Trump born? Where was Michael Bloomberg born? And so on. And then the model executes the verifications and answers the new prompt. So it says that Hillary Clinton was born in Chicago actually, not in New York, as it has said initially. Donald Trump was actually born in New York, which was correct. And then Michael Bloomberg was born in Boston, not in New York. And then you perform a verified response, where you ask the same query, but you incorporate all the information that we have gathered from these two steps. Okay? And when the model answers the query again about which politicians were born in New York, it will say that it was Donald Trump, Alexandria Ocasio-Cortez, and so on. And those answers that it gives in the second response should be better compared to the first response, because the model verified its responses here in the second and third step and tried to answer some questions that were easier to respond to, like where each politician was born. Then the authors talk about the related work and they emphasize the three categories that are used to correct hallucinations. The first one is training time correction, then is generation time correction, and via augmentation. So basically in training time correction, an attempt is made to improve the raw left-to-right generations of an encoder-decoder or decoder-only language model by either training or otherwise adjusting the model weights to decrease the probability of hallucination generations. So basically, you try to modify the weights when you train the model in order to decrease the hallucinations with various methods, which could include like verifying the data it was pre-trained on, or other methods that are enumerated here, like reinforcement learning or contrastive learning. For the generation time correction, a common theme is to make reasoning decisions on top of the base LLM in order to make them more reliable. And they give us an example to consider the probabilities of the generated tokens. We can draw multiple samples from the model to detect hallucinations. For example, you can consider the probabilities of the generated tokens and sample multiple sentences to detect hallucinations. You can also detect hallucination by identifying low confidence scores, and their correctness is checked through a validation procedure. Also, you can use the confidence scores to leverage inconsistencies in LLM's output to detect hallucinations, and so on. You can read this paragraph and see what other methods are used for generation time correction. And the final approach is again to use external tools to help mitigate hallucinations, rather than relying solely on the abilities of the language model itself. And for this one, obviously, is the retrieval augmented generation, or RAG in short, where you use factual documents for grounding. Basically, you tell your large language model to generate text, and you condition the generation of the text using a certain document. And your model should not add facts that are not found in that document. Also, you have chain of thought verification. Also, you can use tools for fact checking, and here they enumerate some works that did that, or linking to external documents with attribution. And now, in the next section, they provide more details about chain of verification. And they say again that they perform 3 steps that we have discussed previously: generate baseline response, plan verification, execute verification, and generate final verified response. And then they go on and explain what each step does. So the baseline response, they say again that we generate left to right as usual using LLMs with no specific tricks. So they don't use anything special here. And while this is the first step in the COVE pipeline, it also serves as the baseline we wish to improve in our experiments. So yeah, basically the baseline response is the baseline for their experiments. And they say that given such baseline generations are typically prone to hallucinations, COVE attempts to identify these hallucinations and correct them in the following steps. And then they go on and talk about the plan verification. So, conditioned on the original query and the baseline response, the model is prompted to generate a series of verification questions that test the factual claims in the original baseline response. Okay? And we have seen how that is done. Basically, you do another prompt to the model where you tell him, give me some verification questions for this query and this baseline response. And they go again with an example, which if you have part of a long form model whose response contains the statement, the Mexican-American War was an armed conflict between the United States and Mexico from 1846 to 1848, then one possible verification question to check those dates could be, when did the Mexican-American War start and end? And they say again that the verification questions are not templated and the language model is free to phrase this in any form it wants. And they also do not have to closely match the phrasing of the original context. Okay, so they are not using templates, they are just sending a prompt to the model and he is free to phrase the verification questions as it wants. That's pretty fair. And also, in their experiments, they perform such verification planning by providing a few short prompt of demonstrations to our LLM. And they display those few short prompts in section A. Okay, and they also say that it's also possible with a sufficient performance instruction following LLM that this could be performed zero shot. So yeah, basically when they send this plan verification prompt, they also give the model some examples, like the example one here, how the verification question should look like. But they also say that you can remove them if you have a sufficiently performant instruction following LLM. So basically if your LLM is good enough. Then they talk about the third step, which is execute verifications. So given the plan verification questions, the next step is to answer them in order to assess if any hallucinations exist. And they say that while such techniques as retrieval augmentation could be used in this process, such as verification via search engine, in this work we do not explore tool use. And they again say that we consider only using the LLM itself in all steps of COVE. Hence the model is used to check its own work. Yeah, I guess it would have been also interesting to see how those models perform if they used RAG. And they say that they investigate several variants of verification execution called joint, two-step, factored, and factor plus revise. and we'll see what each of those means. In the join method, the planning and execution, okay, so steps 2 and 3 are accomplished by using a single LLM prompt. And thus, the few short demonstration include both verification questions and their answer immediately after the questions. So in this step, you also have the verification questions, so VQ, which is one here. I'll put a question mark, 2 here, okay, plus the answers. And you tell the model to do all this in one single prompt. Okay. Then you have two-step, where they say that a potential disadvantage of the join method is that because the verification questions must condition on the baseline response in the LLM context, and the method is joined, the verification answers have to condition on the initial response as well. And this may increase the likelihood of repetition, another known issue of modern LLMs. I don't remember this to be such a big issue in modern LLMs, but okay. And this means that the verification questions might hallucinate similarly to the original baseline response, which defeats the purpose. And thus, they instead separate the planning and the execution into two separate steps, both with their own LLM prompt, and the planning prompt condition on the baseline response in the first step. And the verification questions generated from planning are answered in the second step, where crucially the context given to the LLM prompt only contains the questions, and not the original baseline response, and hence cannot report those answers directly. Okay, so in the second step, which is called two-step, you have one prompt to generate the questions, okay, and in this one you get basically the response, and you also have one prompt to generate the answers. Okay, and in this one you give only the questions, you don't give the responses. No response. Why? Mainly because you don't want your model to get inspiration from its first response. Then the next approach they explore is called factored, which tries to answer all questions independently as separate prompts. And again, crucially, those prompts do not contain the original baseline, as we had here in the two steps, and are hence not prone to simply copying or repeating it. And then they go on and argue why the factor approach is good. So the factor approach has the further advantage of removing any potential interference not only from the baseline response, but also between answer contexts, and is somewhat related to the recent concurrent work of this paper, force of question answering by factor decomposition, hence we adopt their naming. They also say that it can also potentially handle more verification questions, not all having to fit with the same single context. And they say that this is while more is computationally expensive, require the execution of many more LLM prompts, they can run in parallel and hence be batched. So let's first separate those nicely. So this is the joint, okay? This is the two-step approach, and now let's discuss factored. And here the part that modifies is this one here. So instead of having only a single prompt, we have n prompts that we extract from these questions here, and we get n answers. And again, as the authors say, those prompts should not include the original response of the model, because it can influence the result and make the model copy what has been said in the initial response. The final approach is called factor plus revise, and they say that after answering the verification questions, the overall COVE pipeline then has to either implicitly or explicitly cross-check whether those answers indicate an inconsistency with the original responses. And in this approach, we execute this as a deliberate step via an extra LLM prompt, which may make it easier for the final system to reason about this step explicitly. Differently, to answer the verification questions, the cross-checking phase needs to condition on both the baseline response and the verification question and answer. And thus, the author exclude these as separate LLM prompts, one's cross-check prompt for each question with again a set of few short demonstrations showing the desired output. And they give an example. Let's consider that we have the baseline response contain it follow in the wake of the 1845 US annexation of Texas, and COVE generated a verification question: when did Texas secede from Mexico, which was answered with 1836, then an inconsistency should be detected by this step. So in a nutshell, what this approach does is that after you get your questions and your answers, you do another prompt that verifies that those are consistent. So from my point of view, this is just a help step for the final phase, which is generating the verified response. And basically, the factor plus revise approach just gives further guidance to the large language model in generating its response by saying explicitly that this answer is not consistent with what has been said in the original prompt. And now moving on to the final step, where they basically generate the verified response with another step. And they say that finally the improved response that takes verification into account is generated, and this is executed by final fusion prompt, where the context takes into account all of the previous reasoning steps. And the baseline response and verification question answer pairs so that the correction can take place. And they say that if the factor plus revise approach is used from subsection 3.3, then the output of the cross-checking consistency detection is provided as well. Finally, in the experiment section, they talk about the benchmark that they used to measure the efficiency of COVE in reducing hallucinations. And they evaluated this method on 4 tasks. The first one is Wikidata, where they generate question using Wikidata API of the form who are profession, and here they insert the profession, who were born in city, and here they insert the city. And they have Wikidata, where they generate in an automatic way questions using Wikidata API of the form who are some profession, and here they insert the profession, who were born in city, and here they insert the city. And they give an example of who are some politicians who were born in Boston. And they generate 56 test questions, each typically containing around 600 known gold entities. But usually the LLM will produce a much shorter list. And they say that they use the precision metric to measure the performance, in addition to reporting the average number of positive and negative entities produced. So why do they use the precision? I think it would be interesting to provide a little bit more details here. Basically, because the precision tells you how many of the generated answers were true. And if you know, the precision is defined as the number of true positives divided by the number of true positives plus the number of false positives. So when your large language model generates the answers, like for instance here in Wikidata, like person 1, person 2, and so on, you are interested to see which one of these persons actually have this profession. You are not interested in the other metric, which usually comes with a precision, which is recall, which is defined as the number of true positives divided by the number of true positives plus the number of false negatives. And why you aren't interested in this one instead? Well, because as they say, they have like around 600 known gold entities. So they have like person 1, person 2, and person 3, and so on and so on, and Pn, where n is around 600. You are not interested in identifying which of all those people the model has been able to find, which is measured by the recall. Yeah, I thought it would be interesting to give a little bit of explanation about this. I found it really interesting. The authors also test on wiki category list, which is considered to be a harder set generation task. And for that, they use the Quest dataset, which was created using Wikipedia category list. And they convert these category names to questions by simply prepending a name sum. And they give here an example of name sum Mexican animated horror films, or name some endemic orchids of Vietnam. And for this, they create a set of 55 test questions, each one having 8 answers. And similar to the Wikidata task, they also measure precision in addition to reporting the average number of positive and negative entities produced. They also test on multi-span question answering, which is a reading comprehension benchmark, which comprises of questions that have multiple independent answers. And they treat this task as closed book setting, so they don't provide supporting documents, and henceforth they consider a subset of questions which are factoid based so that the base LLM is more likely to be able to answer them. And they generate a test set of 48 questions with shorter answer per span. And they give here an example: who invented the first printing press and in what year? And the answer is Johannes Gutenberg in 1450. The final task that they evaluate on is long-form generation of biographies, and here the model is simply prompted to generate the biography of a selected entity using the prompt "tell me a bio" and then you insert the entity. And they evaluate this approach by using the FACT score, which is a retrieval augmented language model, to fact-check the response, which they claim to correlate well with human judgments. Okay? If you don't know this paper, most probably I will make a video about it and I will explain it more. You are invited to read more about it and the factor score if you want to, but I won't go into details about it in this video. And now the baselines. So they use Llama 65 billion parameters and use greedy decoding for all models. And because Llama 65 billion is not instruction fine-tuned, the authors also employ few short examples particular to each task for measuring performance on each of our benchmarks. And they also evaluate Llama instruction fine-tune models like Llama 2, where they measure both zero-shot performance on the task or zero-shot with chain of thought by adding less things step by step to the zero-shot prompt. And interesting, they find that the instruction fine-tuned models tend to generate extraneous content when queried, so much more than requested. So content that is irrelevant to the question being asked. And this can be a problem for the list-based task, and to deal with it, they add an extra line to the prompt, which is list-only answers separated by a comma. And they also add another layer of post-processing to extract the answer by using an off-the-shelf NER model to further avoid this issue. And finally, for the long-form generation of biographies, they use InstructGPT, ChatGPT, and Perplexity AI. Now moving on to the results, they say here that they focus on answering two questions. The first one is, can COVE efficiently reduce the rate of hallucinatory content produced by the LLM? And the second one is, can COVE be used to fix or remove incorrect generations without decreasing the amount of correct content? And let's look in the results of the experiments to see if we can answer them. So first of all, here we have table 1, where they measure the performance of the models on Wikidata and Wiki category list. And as you can see here, the two-step variant of COVE obtained the highest precision for Wikidata, and the COVE factor obtained the highest performance on the Wiki category list, which is considered the harder task, doubling the precision compared to the original model, which is Llama 65B, which pretty much doubles the precision of the best performing model without COVE, which is Llama 65B. Moving on to table 2, which is here, which presents the results for the multi-spam QA test performance. And again, and here they measure the F1 score, the precision, and also the recall. And you can see that COVE, with a factor approach, improves the results of few shot, chain of thought, and zero shot. Okay, that's pretty good. And finally, in table 3, we have the results of the long-form generation of biographies. And here they measure the FACT score. And here they also put the results of InstructGPT, ChatGPT, and Perplexity AI, but also the results of Llama 65 billion and Llama 2 with 70 billion parameters. And as you can see here, by using COVE with factor plus revise approach, we obtain state-of-the-art results. And here they give more statistics about the FACT score performance distribution across head, torso, and tail facts. I won't go into details about that. I invite you to read. And after these results, they list their findings. So COVE improves precision on all list-based answer tasks, COVE improves performance on closed book QA, and COVE improves precision on long-form generation. So basically, COVE improves the results on all the evaluated tasks. Instruction tuning and code do not reduce hallucinations. Okay. Factor and two-step COVE improve performance. Okay. Further explicit reasoning helps remove hallucinations. And here they say that in the long-form generation task, we also explore more sophisticated reasoning steps in the COVE factor plus revise method. I'm not sure why they don't do that in the other experiments, in the other tasks. Yeah, not sure. Which explicitly cross-checks whether verification answers indicate an inconsistency. And they say that they see large gains in the fact score metric from this further explicit reasoning from 63.7 to 71.4, which is pretty good. But again, I don't understand why they didn't test it on the other tasks. And that this gives further indication that appropriate and explicit reasoning in LLMs can bring improvements in mitigating hallucinations. And also that COVE-based llama outperform Instruct GPT, ChatGPT, and Perplexity AI. Yeah, but that's only on the long-form generation task, not on the others. Okay, and that short-form verification questions are more accurately answered than long-form queries. Okay, that's expected. That LLM-based verification questions outperform heuristics, and to do that, they compare the quality of these questions to heuristically constructed ones in order to measure their quality. And they do that by replacing the LLM questions with templated yes-no questions of the form "Does X answer the question?" for list-based questions with X elements in the answer. And they give those results in table 4, and they say that by doing this, there is a reduced precision with rule-based verification questions. Okay. And that open verification questions outperform yes-no based questions. I am not sure how this is different from the one above. And yeah, here is the conclusion, where again they summarize everything that I've been saying until this point. And here are the limitations. If you want to read them, give them a go. I won't present them here because I believe that this video has already became too long. And with all that being said, I'd like to thank you for watching this video. Please hit the like button if you enjoyed it. And until the next video, I hope you have an amazing time. See you. Bye bye.